Well, thanks for having me speak today. It was kind of a last-minute invitation, but I'll do what I can do. Also, I should warn you in advance, I'm very jet-lagged. I've been up since 2 in the morning, so if my adrenaline rush kicks out halfway through and I turn into a zombie, I apologize. On the bright side, though, this is my first talk not on crutches since the summer, so word to the wise, don't play soccer at Princeton without cleats if the grass is wet. Anyway, I'll just do an outline. This is going to be somewhat of a choose-your-own-adventure talk. Because I'm not completely sure which parts people will know more about and want me to skip, and will know less about and want me to talk more about. Okay, so first, invariants. So I just wanted to philosophize about those very briefly. So generally in mathematics, if you're a geometer or a topologist, you have this sort of paradigm where you specify some space with some data. And then you study structures on those spaces. But often as an intermediate step, it's useful to compute some kind of invariant, which helps to counter-classify these structures, and which is independent of the data. Specifying.
You mean independent of some of the data?
Oh, well, okay. So I should say choice of, right? So for fixed m, right? There are different ways you can go about doing this depending on kind of how fancy of an invariant you want, right? So you could ask an integer question. Right, like how many cells are there in a cell decomposition of your manifold, right? So then you'll get like right? And then you'll get an integer answer. So, for example, like a Euler characteristic. You can ask a linear question. For example, what is the kernel of the Laplacian, right? That's a linear operator. You can get a vector space answer for that. So then you get a vector space. Or you can ask a nonlinear question. And then you get a moduli space answer. And in these cases, in order to get something that's invariant under the data, you have to do something that kind of kills off these extra degrees of freedom. So for example, here you take an alternating sum. Here you take homology. And here you need to sort of take some secondary step. You have to take kind of invariance of this moduli space. So here, a nonlinear question would be like the moduli space of complex structures on something, then you have the Picard-Fuchs equations that's on one linear system of equations. Or you could say, what are the solutions to some non-abelian gauge theory, right? And so then for the invariants, you can do intersection theory on the space, or you can compute characteristic classes, or you can do whatever makes you happy. So I'm mostly interested in this type of invariant because
this can go on and on, right?
Sorry?
The moduli space, you can have a space, you can have a structure on it, and have a moduli space.
Right. I mean, there's sort of no end to kind of how fancy you can get, but there is an end to how powerful you are at computing things, I guess, at some level. Since we mostly understand a lot of things about these more classical invariants, these more nonlinear invariants can tell us things about low-dimensional manifolds that we don't already know. So the key examples in mathematics that we usually use are, so Donaldson theory, which is like, n equals 2 super Yang-Mills. 2. That's equal to Seiberg-Witten theory. And these are 4-manifold invariants, but these have dimensional reductions to 3-manifold invariants. So this one is called instanton Fuller homology. And then there is a dimensional reduction of this called monopole Fuller homology. And there's an alternative formulation of this, which is easier to compute and in practice what everyone uses to compute because it can be made combinatorial, at least for the hat version. It's called Heegard-Fuller homology. And these, at least at the 3-manifold level, not at the cobordism level quite yet, are isomorphic via, they factor through some isomorphism to some other theory called embedded contact homology. So this is wait, no, hold on, sorry. All right, so you'll notice the word Fuller appears in all of these. So I was going to say what I mean by that. So one Fuller theoretic. Now there are sort of primarily two types of Fuller homologies that mathematicians use. There's the one by Atiyah, Fuller, and Witten, which is sort of the dimensional reduction. And then there's Fuller, Gromov, Witten, which gives you Lagrangian Fuller homology. And so these two initial Floer theories are in this first case, and Heegaard Floer homology is an example of a Lagrangian Floer theory. So it's kind of interesting, actually, that there are two different types of Floer theories that are equivalent in this case. So I didn't know, like, do you want me to say anything about what the dimensional reduction of a invariant is, or is it okay? I don't want to like say things that people already will be bored to tears with. Okay, so. So the idea of that is that you have some invariant associated to say an n manifold, and from that you extract some manifold invariant that's one dimension lower. And the way you do this is, so you start out with, so if this is a number counting solutions to my nonlinear equations or my physics, whatever you want to say, on W, then, so this is n, I minus 1, is, it's a Morse homology, like a relative Morse homology. Well, I don't know. Let me just Morse homology. Right, where the critical points are translation invariant solutions on M cross. Can everyone see over here? Okay. M cross R.
I'm not sure about.
You're not sure about saying that? Okay. I can.
No, it's visible.
All right. I think I'm going to run out of space here. Let me.
Isn't that bot Morse or something? I mean, Morse usually assume the critical points are isolated, right?
Yeah. So I mean, it's Floer Morse.
I'm not trying to make trouble.
But yes, I mean, it's not what Morse came up with. It's a
right.
It's a fancier
right.
like yeah. So all right. So we've got critical points are translation variant solutions on M cross R. Right, so I've got some manifold M. Right, and I have these, whatever these solutions are, but they're translation invariant. And then I have a differential, which counts flows. I guess I should say, and in Morse theory, you always have to sort of cut down your space into something you can actually count. So let's say gradient flows between critical points. And so here I'll have some asymptotic solution that looks like a translation invariant solution here, and I'll have one here, and I'll count solutions on this whole space that start here and end here. Okay, and so then I minus 1 is going to be kernel of the, in this points. I guess I'd say like the vector space is over image of D.
this number of, say, of solitons depends on moduli as well, and at which moduli you are. So in this sense, depending in which range of moduli you are, it will be different solitons.
I don't think I understand your comment.
For example, if you change different Morse function, you get a different gradient flows.
Oh, yes, certainly. Yeah, I mean, just like in, in Morse theory or in Lagrangian Floer theory or in this type of Floer theory, you have to make some kind of a choice, like a choice of a metric that specifies your gradient flow, or a choice of, the data that you need here to specify a gradient flow, which I don't want to talk about in depth. And then the idea is that, up to homotopy equivalence, whatever your final invariant is independent of that choice that you made.
So why is this any different from homology that you had before? Just a way of computing it. Is there more to it? Homology of that space.
The cohomology. Yeah, so I mean, this is sort of, like this is like the Q cohomology of VPS states, if you want. I mean, it's on the... I mean, it's something that physicists do all the time. That's why I wasn't sure if you really wanted me to talk about this particular thing.
It's that terminology.
We're a mixed audience.
Okay, so, yeah.
That's something linear now. Yeah, it's not linear.
Yeah, I mean, the idea is you're associating, you start with something that's nonlinear, and then you're associating a linear homology theory to it. Okay, so, okay, so for Heegard-Floer homology, I'm not sure how much you want me to tell you about that either. Okay, I'll tell you some. So first let me tell you about Lagrangian Floer homology. Now this one is sort of more familiar to string theorists in some sense, because what you're studying is the space of paths between two Lagrangians, and I need colors. So let me draw the picture first, and then I'll define some things. Okay, so I've got some space X. I've got Lagrangians L1 and L2 inside X. Okay. And I'm studying the space of paths that end on one Lagrangian and terminate on another one. So are people comfortable with symplectic geometry terms, or should I just define, like...
I think they're familiar.
Okay, all right, I won't do a crash course in symplectic geometry. Okay, so, right, so I've got a symplectic form on my symplectic manifold. It's closed, it's non-degenerate, and my Lagrangian, so L is Lagrangian, if dim L is N, and this restricts to 0. So you should think of this as, for example, this is sort of a canonical example, but you could also think of, say, a real subspace of a complex space if you have your symplectic form regarded as an almost complex structure. So anyway, I've got this theory. I'm studying. Okay. L1, L2. And then I don't have the same type of Morse functional as I do on an ordinary space because I've got this infinite dimensional space. So instead what I have is a relative functional. So I have something that looks kind of like, for an appropriate symplectic form, let's call this, say, D. So, and this will be sort of say, the difference between L1 and L2. And so the critical points, I mean, it takes some work to kind of make this precise, but the critical points. Yeah, so this is some subspace in some infinite dimensional moduli space of paths, right? Are the constant paths, right? Which are just the intersection points, right? If I've got a point here, it's an intersection point, then, you know, it's a constant path. It's not going anywhere. So, and then again, you have to sort of make precise what you mean by critical point of something that's only a relative functional, but that can be done as well. And then the flows are counted by what are called Whitney disks. So if I've got this intersection point here, then, and I've got some other intersection point here, then I have some path from X to Y along here, and I have, oh wait, some path. So this blue is inside this Lagrangian. And then I've got this other path, which is inside this Lagrangian. And traced out here is this little disk. And if this has, there's a grading on this space called the Maslov index. And if this disk has Maslov index 1, which means that the grading between these two critical points is of difference 1, and if this disk has a pseudo-holomorphic representative, then then it's counted in this Morse differential here. So so I've got, you know, dx looks like some. So I've got like. So these are Whitney disks, so Maslov index 1 and pseudo-homomorphic. And then y. So it's like y. Okay.
Why do you restrict just to disks?
Sorry?
Why do you restrict to disks?
Well, because I've only got 2 points. So here I'm just doing ordinary Lagrangian full homology, and there are only 2 Lagrangians. So there's a fancier version called the Fukai category where you have arbitrarily many Lagrangians. And then, so, okay, so.
He's asking why couldn't a circle bound a higher genus?
Why do you take a higher genus?
Why do you bound a higher genus? So I think that's sort of the choice you're making on what types of flows you're counting, right? So if you allowed more general surfaces between your points, then you'd have some larger number of flows that were allowed. And
but that's more natural. Gromit theory would allow arbitrary ones.
Okay.
Right? I mean, you don't
Yeah,
restrict the genus.
That's fair.
In fact, these kind of things are related to the invariants I was talking yesterday was it when we were talking about Hovanov's other graph things? These are the kinds of objects that you'll be counting. But the arbitrary genus, and the genus will represent a spin. So physically that's important to include in that context. So.
Okay.
Then it wouldn't be Whitney.
Well, okay, it would be Witten or whatever you want to call it.
Yeah, I mean, it would be
Whitney disk was needed to eliminate these 2 points.
Eliminate
the intersection points. You can deform one of the maniples, one of these Lagrangians along this path, along this disk to eliminate the points.
Because what you're trying to do is kind of get rid of excess intersection in a way, right? You know, if I've got some disk like this, then I can pull these apart. And these points sort of didn't deserve to exist to begin with.
Okay, but if that disk had had a handle, then the handle could have potentially attached to one side or the other.
Right.
Right? So you could in principle
So
handle
in principle, you could try to formulate a theory that had a more complicated differential.
This hasn't been done.
Not as a Lagrangian blur theory that I'm aware of. I mean, you know, I'm not an expert on sort of generalizations of Lagrangian Floor homology or Fukai category, so I don't know. I don't want to make any definitive statements on what has or hasn't been done,
Okay.
but at least the classical version of Lagrangian Floor homology, you only use Whitney disks. So anyway, where does this come into play in Heegard Floor homology? What number is that? 2? Okay, so here, this was motivated by a conjectured technique for an alternative formulation of instanton Floor homology, called the Tia-Floor conjecture. So the way this works is, given any 3-manifold M, I have what's called a Heegard splitting. Where I, depending on which direction you're going, so I can either think of starting from my Heegard surface and choosing some collection of compressing disks. So here's the stupidest one you could have would be a Heegard diagram for S3, right? So if I have compressing disks that look like this, and sorry, this should be inside the surface, not outside there. Right, so the idea is this U alpha is the handle body that's given by attaching 2 handles, so attaching disks to each of along each of these curves, and then attaching a 3-ball inside, like a 0 handle inside. So think of this as like a solid. All right, so now there's another ingredient here, Rx, which is the space of representations from I1 of x into, well, in this case, SU2. If you're doing, but you could do a representation variety for other groups if you wanted. Now, why is this relevant? Well, that is the same as the space of flat SU2 connections on your space. So, actually, let me do a little. No, I won't do an interlude on that yet. Let me finish this one. Okay, so there's this conjecture. That the instanton Floer homology M is given by the Lagrangian Floer homology of R of U alpha with R of U beta, because R of U, whatever this is a Lagrangian subspace of R of so both of these, alpha and R beta sit inside this space, and so the idea is you're trying to extract representations in the whole space from representations that kind of are compatible with each other with respect to the T-guard diagram.
Just let's see, am I getting the dimensions right? So U is two-dimensional, or for U is three-dimensional? What is U here?
Oh, so both of these are three-dimensional objects, right? This is like the filled in, the solid one.
Okay. I see.
But I've killed off like half of the homology when I go from this surface to here, or like half the generators of the fundamental group. So anyway, I end up restricting to a Lagrangian subspace when I'm looking at the representation variety. So there's some amount of progress that's been made on this recently, but I'm not going to talk about the Atiyah-Floer conjecture for SU2, because what Oswald and Szabo did is they tried to think of something that would be like the Atiyah-Floer conjecture, but for Seiberg-Witten theory.
Sorry, I'm still confused with dimension. M is dimension 3 or 4?
Okay, sorry. M is dimension 3.
Then what do you mean by instanton? I'm a bit confused.
Okay, so by instanton, I mean
M times
the
R?
M times R.
M times R,
that's
right.
it.
Trans-Lyman kind of action.
Right. Yeah. So I was. Yeah. Just to be specific. I mean, so here, like I've Donaldson. Right. So for the Lagrangian is some gauge theory Lagrangian. Here, it's not really so much a Lagrangian theory. When I localize it, I've got anti-self-dual connections. Here, when I localize it, I get something that looks like, in math language, this, and in physics language, more like this. And then I have the Dirac operator. I'm just going to do 0. But then when I take the dimensional reduction, my Lagrangian is like a Chern-Simons here, and it's a Chern-Simons Dirac here. And when I localize to BPS states or solutions, whatever you want to call them, I restrict to flat SU2 connections on my 3 manifold. Whereas here, I just have solutions to the monopole equations, which looks like a kind of close to this, but a little bit different. They're not any prettier. So that's part of why I'm talking about Heegaard-Fleur and monopole Fleur homology today, is that this is a very nicely mathematically interpretable answer, right? I mean, there's, here, let me just, for completeness, going to say theorem by Thurston. So if M is, let's say, closed, oriented, irreducible, so that means no essential S2s, and atoroidal, so no essential tori. Then M is either hyperbolic or cyberfibered. So that's 1. And 2, M, so if M is not a non-trivial lens space, which is like this one exceptional case where it doesn't work and you have to use Reidemeister torsion or something else to classify the space, then M is uniquely determined by its fundamental group. So this kind of an answer where we're classifying flat connections on this space, which is a very nice geometric thing, and where this is also isomorphic to the space of irreducible representations from pi 1 into SU2, because I can specify my flat connection by the monodromy what my transformation functions are as I go along loops in the base. So this kind of an answer is about as nice as you could get for something that has good interpretations. This side is not, and is very much up for grabs, like what it actually means for 3 manifolds. I mean, for 4 manifolds, it's kind of viewed as a way to distinguish between smooth structures, and even there we don't know exactly how uniquely it distinguishes. But anyway, so where were we? Heegaard-Fleur, Atiyah-Fleur, motivation, blah, blah, blah. Okay, let's go over here.
So this, just to make sure, this Heegaard-Fleur involves just disks involved only again?
It's Lagrangian Fleur.
Yeah, it's Lagrangian. This is
H for homology, not for Heegaard.
Yeah, it's not. Yeah, that's very confusing. In Heegaard-Fleur we use HF for Heegaard-Fleur, but then there's also HF is this sort of classical notation for Lagrangian Fleur homology as well. So here I mean Lagrangian. You know what I'm saying. Okay. So for Heegaard-Fleur homology, instead you have this Seiberg-Witten theory, which has like a U1 gauge theory, but with a spinor component. And so if you tried to do some kind of a U1 representation variety here, instead you would get like it's abelian, so it's just generated by the so R of U alpha would just be equal to T alpha, it's a product of these different alpha curves, and R of U beta would be equal to T beta, product of these.
You'd probably switch the curves. Right?
What?
RU alpha would be the product over the betas. Because you kill.
Oh, okay. You're right. Fair enough. Yes. So, so instead, we're looking at a Lagrangian Floer homology of these tori inside the space of. Okay, so here. If I were just 1 foot taller, I could use this board so much more efficiently. Okay, so I've got a Heegard splitting. And I have a Heegard diagram. So let's say a base point. So a Heegard splitting, I just specify the handle body. So Heegard diagram, I tell you actual curves, like I tell you what the compressing disk boundaries are. So the way I like to describe this is to make a sort of an analogy with what you do in Morse theory versus what you do in Heegard Floer homology. So here's Morse theory. So, so I would say like on M. So here we would have points on M. Here I'd have G tuples of points on sigma. So and I want unordered ones. So this is equal to the space sim G of sigma, which is just sigma to G of sim. And since sigma is two-dimensional, this is just a smooth space. There's nothing, this isn't an orbifold or anything. This is just an ordinary honest-to-goodness manifold. Because locally, when you perform that quotient on the complex plane, nothing bad happens. So my chain complex then is critical points at F, where F is my Morse functional on R. And right, so you could view this if you wanted as a span of these individual, so let's say like alpha I and beta J. Although I don't know, maybe I don't want to get into it. So there's sort of a dual description of a Morse functional in terms of a handle decomposition. And so you could sort of regard this Heegard this Heegard splitting as providing a handle decomposition for your three manifold, and then so the critical points corresponding to the handle decomposition corresponding to your Morse function are still given by these intersections of these alpha and beta curves. But I don't know how much it adds to write that out there. So over here, Hilbert Fleur is span of T alpha and T beta, where T alpha is the product of these alpha i's, T beta. Product of these beta i's. Okay, so, and then when I want to look at flows, I'd have some gradient flow line here. Wait, so Q, right? So this would be like my gradient flow line. And of course, I have one over here too. Here I've got a disk that I'm mapping into sim G of sigma. And this will be in pi 2 of xy, right? Because it's like a disk. And you know, this guy belongs in T alpha and this part belongs in T beta. So this is some Whitney disk. And yeah, I don't know. Let's see. For x and y. Okay. So, and then all that's really left to do is tell you the differential, which is kind of what you expect, because it's just a Lagrangian Floer homology. Right. So. Here, for the Morse differential, I've got D, P is sum over times the class Q, right, for so I'm looking at sort of the moduli space of flow lines that, right, it should have dimension 1, and then I mod out by translation invariance, and I get this differential. This is sort of this, you know, standard Morse theory, right? So in Hilbert Floer homology, and I have this extra little condition that where I exclude the base point. There are different ways of treating this base point depending on what flavor of Hilbert Floer homology you're working on. But then I also say this is pseudo-homomorphic. And here I say that this is a gradient flow. At least when I'm looking at the moduli space. So remember how I said that you have to sort of choose some extra piece of data, like a metric specifying your gradient flow, or a complex structure, or symplectic forms, specifying what it means to be pseudo-holomorphic, and that makes your moduli space manageable so that you can count flows. So that's what you have to do here. And anyway, then the so Morse homology of M then is just the homology CF Morse, D Morse, right? And then Hilbert Fleur, is and this is also equal to, I mean, I kind of showed you in gory detail what this is just, this is the Lagrangian Fleur homology of T1 alpha and T beta.
What is this condition on NZ?
Oh, sorry. So this is saying the intersection of, so I've got this base point Z somewhere, it's just a point somewhere in my Hilbert surface. And then so there's also an image of like the diagonal associated to Z that's in my,
Sure.
well, or any points inside the symmetric product. So anyway, I'm just demanding that when I have these little domains in the Hilbert diagram that are connecting alpha to beta, I don't have any intersection of this domain with this. That's another thing that's a little bit subtle is with Hilbert Fleur homology, working with the actual Lagrangian in the actual symmetric space is not really a feasible thing to do. So instead what you do is you work with sort of domains that look like...
You're saying Z is not in a bigone, or what?
Z, well, so what you actually have is something like this that lives inside your Hilbert surface, right? So, and this might be, say, alpha 1, alpha 2. Wait. And then these other guys would be my betas. And so I'd have, these are points that belong to X. Part of some four tuple that, so this whole four tuple lives in my, is a point in my symmetric product if G equals 4 here. And then I have, well, Y's here. And so what I, in practice, end up doing is looking at these domains and then determining whether a domain like this corresponds to an actual Whitney disk in the regular thing. And in principle, that requires solving partial differential equations, but people have been clever and figured out combinatorial ways to construct Hilbert diagrams so that these questions are combinatorial and you don't have to solve any partial differential equations to work out what you're doing. Okay. So now we get to the sort of actual talk. I'm not going to really talk about the construction of Hilbert Fleur homology in the talk. I just thought, you come across it some and like, well, if you look in the mathematics literature for people trying to get things in multiple Fleur homology, then they're usually doing Hilbert Fleur homology. And Tom Rovka, if you're watching this, I'm sorry. But so it's sort of, for cultural literacy reasons, useful to kind of have some idea of what it is. But then the question that I'm interested in is what does this invariant actually mean for three manifolds, right? So Hilbert Fleur theory does have some applications. Okay, so let's say we're at 3 now. Okay, so there, especially if my three manifold has positive first Betty number. So 1 and 0, then in principle I could have a non-trivial Thurston norm. So if this happens, then Hilbert Fleur detects the Thurston really dual Thurston norm for M. And do you guys know Thurston norm? Okay, so let's say so let's say alpha H2 of M primitive, the Thurston norm alpha written is so it's a way of sort of telling you what the minimal genus is of a surface representing your second homology class. And in monopolar homology and in Heegard-Floer homology, there's something called the Injunction Inequality, which says that your okay, so inequality. It's kind of like a cousin of Riemann-Roch. But in three manifolds, there's no concern about self-intersection because if you have an embedded surface, then it has a trivial normal bundle. So you just have and the spin C structure S is, I kind of suppressed this, the fact that this filters, the chain complex splits according to this further I'm missing the word that I want, but thing, which is this spin Z structure. So, which, as an affine space, is just isomorphic to the first homology. Anyway, so.
This definition of norm satisfies the inequalities that you expect for norm?
I'm sorry, what?
This definition presumes satisfies the norm inequalities?
Yes, so this is kind of, it holds for alpha primitive, and that kind of makes sense, but the theorem of Thurston is that if you don't demand that this is primitive and you use this norm again, then this extends in a way that's linear and gives you an actual norm. So I guess I should say more generally, applies to alpha, not primitive.
A norm or a semi-norm?
Sorry?
Is it a norm or a semi-norm?
Well, so it depends on
Atoroid.
whether yeah. So if you have an atoroidal manifold, then you don't have to worry about this. You will always have. So if you have an irreducible atoroidal manifold, then it's an honest norm because there are no things with. This will never be, this will have no kernel. If you do have tori, then things or spheres, then things get ugly. But why would you want to do that? Because there's a JS decomposition. I mean, we don't need that. Okay, so this is 0 if the first term class is spin C structure. This is greater than minus this. So if you this tells us that the Heegard-Floer homology sort of vanishes above a certain genus for my space. But then there's also this result of Gabai, and I guess probably uses some more slowly. that if so let's see. So if alpha H2M has genus minimizing representative sigma alpha, say, then there exists a top foliation oriented one, in fact. I'm going to talk about co-oriented top foliations in just a minute, so I'm not going to talk about what they are now. With sigma as a leaf. And you can use this to show that the Heegard-Floer homology does not vanish if, so let me see. Here. That's an even stronger statement. It's not vanish if so anyway, so you putting these things together, you're able to use Heegard-Floer homology to tell you what the Thurston norm is. So that's one application, but it's vacuous if I have a rational homology sphere, right? So the Thurston norm doesn't exist if B1 of n equals 0, because that implies that my second homology is 0, and there's just nothing to Thurston norm.
Well, you still have the zero norm in the empty vector space, but
that's true. I should say there's nothing non-trivial that exists.
There you go.
Yes. Since when are you pedantic? Anyway.
I teach math.
Okay, so the other ones are that there's a version of Heegard-Floer homology for knots, which is almost the same as the one for closed manifolds, but there's an extra base point, and then the pair of base points specifies a knot by telling you kind of how you have a flow line in one direction from the point from one point to the other. Okay, so all right, so I've got Z, I've got W, and I've got my alphas. So my knot has to go from Z to W kind of inside the U beta handle body. And then, so it can't cross any of the alpha curves. And then it goes from W to Z inside U alpha, where it doesn't intersect any of these. I mean, this is a stupid example because I've just drawn the Heegard diagram for S3 and I've drawn the unknot. So it's, but you know, so it's computed the same way. You just have two base points and it's a minor variation. So anyway, HFK for knot K in S3. This is defined for knots and other manifolds, but here. Detects if K is fibered, and it detects the genus of K. which means the minimal genus of a Seifert surface for K. Okay. So the Knopfler homology tells us a little bit about the space. When I have positive first Betti number, I know something about the space from there. But in the case that M is closed, oriented B1 equals 0, then it's harder to know what the Hilbert homology is telling us about the space. So one way of figuring out what Hilbert homology might be counting is asking when it vanishes and then seeing what other structures disappear when it vanishes. So definition, M is an L space if HF if M is 0. And here, this little red is a decoration that, so there's Hilbert homology has, it always has one reducible class in each spin C structure. So you can, if you mod out by that, you get what's called the reduced version, and then you don't have this sort of trivial thing that's left over, and then you're actually figuring out if you have anything non-trivial. So there's a conjecture that nobody really believed for a very long time about what sort of things might correspond to L spaces. Mentioned it. It was stated formally as a conjecture in a paper by Boyer, Gordon, and Watson for the left order case by Andros Duhaus for the Lagrangian case. So M irreducible. Oriented. Following your cover. So M is not an L space. M admits homologation. I run it then. Admits left definition. And low order. So let's call this a left order, and this is CTF. So what are these things? So a foliation is, I mean, if you like, it's sort of a locally defined atlas that is foliated on your manifold. So it's kind of just, so a foliation is, let's see, M charts, say, RK, N minus K, and then with sort of a compatible gluing conditions that preserve this decomposition on one side. So it's almost like a bundle, right? So a bundle, what you do is you specify what a neighborhood of a fiber looks like, right? I've got a fiber, I've got some neighborhood of a fiber, which is like F cross U, where U is in the base. And then I have my transition functions look like an automorphism of a fiber cross some stupid transition function on the base. So in a foliation, instead I have a neighborhood of a point, which looks like some RK cross U. And then I have the same thing. It's just this doesn't have to extend as a neighborhood of a fiber. It's only in a neighborhood of a point. But bundles with flat connections give a very good example of foliations, right? So an example flat connection has foliation. So I guess you could say it's a dim B foliation. By parallel transport. Right, so I've got my base, I've got my fibers, and then I've got, I specify the leaves of my foliation by following my vector space around according to the connection. Okay, sorry, this is kind of sloppy, but I don't want to run too far at a time. And a left order, it's just what you think. It's so, it's something, I have some order in my space, if and only if, say, L, G, less than L, H. So another, so let me see, theorem, and I'm forgetting off the top of my head who's, so there's sort of a bijection up to semiconjugacy, left orders on G for G countable, and representations homomorphisms of the real line. So so there's sort of this dynamical way of taking an action on a real line and extracting of your group and extracting an order on the group, and there's sort of a way of going the opposite direction as well by taking lexicographical ordering. So what this means is that a left order on G also could be described as an R bundle over M. So if G is pi 1 of M, then I have some foliated R bundle over M with foliation specified by this representation, and except it's not a line bundle. This isn't linear. These are actual just homeomorphisms. Okay. So, but anyway, so before I talk about any results related to this, I wanted to say that it's not so off the wall that you would expect objects like this to appear in this context, right? Because in the Seiberg-Witten case, we don't have flat connections. So we don't quite expect representations of a Lie group. But maybe we could be expecting, representations of some fancier group instead. Or, there's... and we don't have... similarly, we don't have... a foliation is a generalization of a flat connection on a bundle, but it's more general. So these are two sort of different ways of generalizing the notion of like flat connections on bundles in some sense. So it's conceivable that they could be the correct generalization. I didn't tell you what it means to be taut. So if my manifold is atoroidal, then you can say that it means that I don't have anything, I don't have any what are called RAID components, which is kind of like a cheating way of turning a singular foliation into an ordinary foliation. So foliations themselves are too floppy. Like up to homotopy, they satisfy an H principle, and if you're doing it up to isotopy, there's too many of them, and it's ugly. Like there are a lot of them even on the 3-sphere. So, anytime you have a lot of something on the 3-sphere, you're not telling you about the 3-sphere anymore. But top foliations, there are no top foliations on the 3-sphere. So that's a better thing. Yeah. So. So this conjecture kind of fizzled for a while, but then more recently there's been progress. So, well, okay. So this was proved to be true for Seifert fibered spaces about 10 years ago, maybe. So I proved that it's true for graph manifolds. Yeah. So. And moreover, the space of graph manifold L spaces / not top foliated things / not LO things is cut out by explicit set of inequalities. And they have some form. You have some kind of set labeled by K of which, I have some recursive formula where I have my graph. Oh, sorry. So graph manifold is plumbed manifold. Like, it's, yeah. So if this is like the Seifert data for my Seifert fibered space, and then these are like recursively defined L space interval endpoints from this formula. There's something like this, and there's another one for a maximum. And anyway, you can like sort of recursively compute these endpoints, and then at the end of the day, the final one, if you have you've got an L space. And so you can use this very powerfully to compute the spaces of L space surgeries on algebraic links and all sorts of things that like are related to graph manifolds. But more interestingly, so the way that I went about proving this. Oh, and also I should say, so this part of the theorem, there's an independent paper by Hanselman, me, Jake, and Watson, they somehow wanted to have a version that just had the equivalence without the moduli space thing. Anyway, this set, which, so for Seibert-Seibert spaces, this set that looks like is this sort of ubiquitous collection of numbers that appears at endpoints between surgery slopes that are classifying the appearance and disappearance of these different objects. So if you sort of look at the minimum of this set, then you get the space where you have just L spaces. But if you look at this set overall, okay, actually I should tell you where this set is coming from. So if I'm doing surgery on some manifold, so I have some boundary that's a torus, then homology it's torus. Looks like sort of rational numbers sitting inside a circle. And so I've got this kind of this circle of slopes in which I can do surgery. And it turns out that when I'm doing surgery on a nut or surgery on a fiber in a Seibert-Seibert space, as in this case, I'll have some interval of surgeries where I have L spaces. And then I'll have, and then I'll hit one of these points and I'll get a new Heegaard-Flirt class. And then I'll hit another point and I'll get another Heegaard-Flirt class. So the Heegaard-Flirt homology changes discontinuously each time I hit one of these endpoints. And the same thing happens for these top foliations and these left orders. There's a sort of dynamical description of representations of the orbifold base into homeo plus of R that's classified by a problem that has endpoints that look like this. And so you have the same story of getting these new objects appearing there. So for Seibert-Seibert spaces and also for negative definite graph manifolds, I can construct a correspondence between classes, not just at the L space level, but as you sort of look at the entire set of classes, you can extract which ones correspond to top foliations and which ones top foliations and L spaces for these Seibert-Seibert and graph manifolds. And the cute thing is there's also an algebraic geometry story about this. So if L space conjecture, there's one more version here. So if M is negative definite graph manifold, so that's like a negative definite plumbed manifold, then it's the boundary of some complex surface. You can, it's not really very legible. Anyway, there's a theorem of Nimithi that this is the boundary of the minimal resolution of a rational surface if and only if M is an L space. And there's this model by Pinkham and Dolgochev where you can sort of formulate the coordinate ring and, I don't know, you put some point divisors on an exceptional curve. And anyway, you get these numbers back when you're computing the geometric genus of the singularities that correspond, of which the three manifold is the link. So what am I trying to say? So anyway, these are interesting objects in mathematics that appear to be related to these gauge theory things. So it would be interesting to know if there's any kind of, physical thing that they correspond to. And let's see, I've got 5 minutes left. So there's one more question that I kind of.
Can I ask before you?
Yeah. Okay. Yeah.
Are there a finite number of points in that circle that you have jumps?
So they're finite outside. So there's a distinguished point when this is the boundary of a 3 manifold that's a torus. There's a distinguished slope in here, which is the rational longitude. And that's the kernel of this map when you just look at the non-equation pieces. So outside a neighborhood of the rational longitude, there are only finitely many points, but they accumulate on the rational longitude. Yeah. So so for the surgery story, it's kind of sad that they're, you could give a whole other talk about where you get these sorts of things. I mean, for L spaces, surgeries on L spaces, you can compute it just using exact triangle constructions and working very hard. But you can also look at the wrapped Fukai category, the punctured torus, corresponding to the boundary of a 3 manifold with torus boundary. So if M has manifold with torus boundary, if M is a manifold with torus boundary and is compact and oriented and all those things, then there's a sense in which you can associate the Heegard-Fleur homology of M to an element of the Fukai category of the punctured torus. So if this is some kind of cylindrical cover, you get some kind of curve. And then you can, when you do surgery, or if you glue some other manifold with torus boundary to it, you intersect the Lagrangian curve corresponding to that thing on top, and then you do Lagrangian Fleur theory. You just count these points, and that gives you the Heegard-Fleur homology of the union. So anyway, there's this whole pretty picture of this to compute Heegard-Fleur homology. So I would be interested if there's any. I mean, like, so the mirror of this object is like a cusped, like the derived category of this cusped curve thing. So, like, I'd be interested if there's any kind of physics story about a mirror symmetry dual to this construction. And that's probably good enough for now.
Any questions?
So one physically motivated question and comment. So first, if you consider Heegard-Floyd for a knot, and when you consider Poincare polynomial, it provides generalization of Alexander polynomial for the knot. So, there is a very simple representation of Alexander polynomial in terms of monodromy of homologies.
Like Campillo Delgado-Zade?
And is there some generalization for? Is it possible to generalize this formula due to monodromy in a refined case?
Yes, I could give another talk about that if you want, but it's a long answer, so I could talk with you about it.
One more comment, and there is some duality between pairs of integrable system related with modular space of flat connection, one of Ruiz-Nice type and another of spin chains, and there is duality between intersection of Lagrangian manifold in one system and Bertrand-Zatz equation in the second one. It provides, therefore, it's suspected that there is a non-trivial relation between Heegard-Floyd on one side and soliton, which interpolates the solution of Bertrand-Zatz equation on the other side. So it's another counting problem which could be related with all this stuff.
Okay. I'd be interested to talk with you more about that. Thanks.
Any other questions?
So I guess going back to the beginning, this is something we talked about maybe a year ago, but these invariants, I guess, are the BPS spectrum, some Q cohomology. So does that mean that it's expected that there's some kind of unitarity in this TQFT? I'm not saying, I mean, you didn't talk about TQFT, but there's lurking here some attempt at a 4D TQFT. Just wondering,
Yeah.
maybe ask the room, ask you, like, is there?
I don't know. I mean, like, so foliation can be described as a kernel of, so if it's smooth enough, kernel of some one form such that alpha, what is the alpha? Is 0, so non-vanishing. So, I mean, this is the, this is abelian-Chern-Simons theory, but that only gives you a foliation, not a top foliation. So, so that kind of part is sort of a unitary question, but the extra constraints, I don't know if they are or not. Also, this bit about the, representations in homeo plus of R, like there are smoothly subgroups of homeo plus of R where you could ask questions about unitarity, but homeo plus of R is not a unitary group. So, so I don't know if there's some non-unitary generalization that needs to be invoked in order to understand physically how that would correspond to something. I don't actually. A physicist would know better.
This is an illustration to this that we studied with one company. Non-unitary Chern-Simons did come up, and we think it's related to this story.
I mean, my motivation is this, as you pointed out, that the homology is the kernel of the Lagrangian, well, the Laplacian, dV star plus C star D. So this is a linear problem, and I guess you can hope to understand like how good is this linear problem or how bad is it, and it has to do with the spectral properties of that Laplacian. And I guess I'm just hoping to get a foot in the door and just like I don't know if there's any perspective that might help understand that spectrum of this operator. So anybody.
Any other questions? If not, let's thank Sir again.